Welcome to State of Simulation, the podcast all about multiphysics simulation, where we stay up to date with what's working, what's not, and what needs to change. Each episode features an open conversation with the engineers and technical leaders shaping the future of physical product development. I'm your host, Jukka Knutinen, and in today's episode we're speaking with Juha Riippi, CEO and co-founder at Quanscient, about MultiphysicsAI, a set of features in Quanscient and Allsolve that turns large volumes of simulation output into surrogate models for design exploration, inverse problems, and optimization. In this episode, we cover the fundamental questions of Quanscient Multiphysics AI. What is it? What does it do? Who is it for? How does it differ from the other AI-driven simulation approaches out there? And how you can start using it today. Overall, this episode contains everything you need to know about the approach now and where it's headed next. Without further ado, let's get started. I guess the first burning question is that what is Quanscient Multiphysics AI?
Well, Quanscient Multiphysics AI is a set of features that we're building for Quanscient Allsolve, and basically the concept is simple. Quanscient has, since the start, been our unique kind of value proposition has been that we can massively increase simulation throughput by having the fastest multiphysics solver out there, but also the most scalable by using cloud computing. And during, I would say, the last 18 months, we've started to realize that this large volume of simulation data is actually very useful for AI training or machine learning training. So what Quanscient Multiphysics AI is, in a nutshell, is giving our users capability to easily train machine learning models based on a lot of multiphysics simulation data, which they can then use to solve inverse problems or solve complex optimization problems using strongly coupled multiphysics data produced by our cloud solver.
Could you go a bit more into details of how does that work? So how does the process look like from the start to the end, so to speak?
Yeah, absolutely. So I think maybe to get into that, like you could think of it this way, like that traditionally simulation tools are used as a validation tool. So step one is that an engineer designs something. Step two is typically that they run a handful of simulations to validate how this works. And then you iterate on that until you have a design that matches your specifications. Now, what this massive throughput in simulation output and multiphysics AI can change in that is that actually you use automation optimization algorithms and, for example, parametric CAD geometries to run thousands of simulations from the get-go. And that's already valuable as such. You're getting a lot of insights about your device, a lot of different design variables are being evaluated. But then you generate that massive pool of data, kind of a large data lake, so to say. You take that data and train a machine learning model from it, which is effectively a surrogate model. And with that, things get interesting because now you can flip things around. Instead of asking the question that I designed this thing, how does it work? And then iterating, you can start asking questions like, these are my design KPIs. What would be the optimal design that produces that? And if you have a large enough data set and high quality AI models, that's exactly what you get from that. So that's kind of a new step in the process. And then finally, you'll probably, with this, you can do large scale design exploration, kind of see what could be the optimal designs for different design variables and KPIs. Now, as the final step, what you can still do is you still probably have a lot of options on what you can do. You can validate this narrower pool of high quality design candidates again with deterministic numerical simulation data. But that kind of when you're able to flip things around like this, you might save months of iteration time in your R&D. You'll be shipping your products to market faster. You'll actually be delivering potentially optimal solutions to your design problems instead of kind of local optimum that is based on iterations and kind of a evolutionary improvements for your products. And you might even optimize for things like if it's a semiconductor or MEMS device, for things like yield, which is kind of goes directly into your profit margins. So those are the big benefits and how it works in a kind of in the big picture.
So you mentioned a couple of examples or applications there, but what kind of specific applications or use cases is this good for? And do you have any examples of those?
Yeah, we've been working on quite a few. So kind of on the high level, we have examples on PMOD optimization. So kind of with that would be basically an optimization problem where your designers would be able to create a Pareto front for two different KPIs that are kind of in conflict with each other, which would be the device sensitivity and the frequency bandwidth. So those are kind of like for a petrol engine, that would be performance and fuel efficiency. These are two design variables. You cannot optimize fully for both. There's a Pareto front that kind of gives you the optimal design on this curve. Depending on which one do you want to emphasize on your design. So that's one of those. Then we have piezo material characterization. So solving an inverse problem on what kind of material, piezoelectric material properties will give you the design that you want for your PCT material problems related to ultrasound again. We're working on an electric motor hub shape optimization, inverse problem again, kind of starting from what kind of torque output you'd want from your engine, what kind of hub shape would produce that. Another one would be a microspeaker example, optimizing the sound distortion and intensity balance. So things like this we've been working on. Actually, something for superconductors also coming up, again, this time for material characterization.
All right. So I think many people have noticed that a few other simulation platforms or simulation providers have also came out with their own AI-driven workflow. So how is this different?
Well, I mean, fundamentally, the AI that's used here is not so different. And there's obviously companies that are kind of really dedicated to just the AI part of this, like MEAI, PhysicsX, Neural Concept, such. But how we really differ and where we shine in is the ability to generate these large volumes of strongly coupled multiphysics data, which is kind of unheard of in the industry. So that training data that we can utilize is our unique strength. And actually, we're very much open to partnerships with companies, as mentioned before. So kind of combining their AI expertise with our capability of producing a lot of training data. So that's really the unique aspect of what we do here. And when you have that, so you can actually use, like when you have access to a lot of high quality training data, you can actually use relatively simple AI techniques like neural networks that have been around for quite a few years already. So that really opens up what you can do and what you can achieve with these models.
So you mentioned the training data many times there. I think many people might have this fear or concern that when it comes to AI, sort of expanding on that, how can you trust it? So how can you know that the AI is just not hallucinating when it is coming up with this, either expanding the training data set or then coming up with the predictions?
So yeah, that's a valid concern, and it can obviously happen. And particularly if you ask the AI to do something that's kind of well enough beyond the training materials that have been provided for it. To counteract this, of course, what you can get from these algorithms is sort of the confidence score on the evaluations. So that's one thing. You can kind of get this explicitly, that how well the AI predicts that this will likely be a match. And what you have to remember with AI, that it is a probabilistic method. It's never deterministic like numerical simulations. So it's always like a good approximation. But then recognizing when that is enough, when you're doing kind of like design exploration, typically it's enough to be good enough. You don't have to be 100% or 99.999% accurate with those. And what you always want to do, obviously, after that is actually validate with numerical simulations. So AI is great in exploring a vast design space, what could work super efficiently. But then you can always go back. You can always validate, kind of limiting down the number of design candidates that you have.
Okay, so this multiphysics AI, this was released just last week. So what will happen from here on out? So this sounds like a interesting approach for sure, but how will it shape now the engineering workflows going forward? Let's say 1 year or even 5 years.
Oh, for 5 years I'd need a crystal ball, but let's give it the best guess. So what we have now are well-defined workflows on how to do this, and quite a few examples. And we're working with some early customers kind of on piloting the work and getting the feedback, taking that feedback and helping us improve and shape how exactly it works in a more finalized, streamlined workflow right within Quanscient and Allsolve. So that's already doable, but it's a little bit manual at this stage. And we're typically involved, kind of working with our customers on these topics. Down the line, kind of when we're looking at second half of next year, that's when we really are starting to have a finalized workflow. So you can just use the graphical user interface, select what data you want for the training, run the trainings, and then use the surrogate models right there in our platform. So that's kind of in the very immediate future. And of course, kind of expanding on the set of examples. So we'll have actually ready-made, pre-trained surrogate models that our customers can utilize directly, which can be a good starting point for their own designs. But looking down the line, like I think really the workflow that I described very early on, so always starting with generating your training data, training your machine learning models, using that to solve, like kind of flip engineering around to solve the inverse models, and then validating again with numerical simulations. So that's where we want to get to. And effectively, I think one comparison could be where kind of hardware development is going, that automation will increase. So you'll have computer-aided engineering simulation tools like us talking directly to computer-aided design CAD tools. And effectively, kind of, let's say 5 years from now, how this all could work is that engineers are kind of working on parametric CAD design models. And there's an automated pipeline that is constantly building the data lake of that kind of physics-based data they have, might be constantly training AI models that can be used for validation and kind of coming up with those optimal solutions, inverse problems. So I'm coming from a software engineering background, and actually in software, well, maybe not solving inverse problems, but we have like continuous integration pipelines. You write a piece of code, maybe use Gen AI to use that piece of kind of to speed up your development. And then you have a continuous integration pipeline that automatically runs all your tests and kind of deploys it into production at given intervals. So something similar definitely can be done for hardware with these new technologies. And Maybe one thing we haven't covered at all, we've been talking about this multiphysics AI, but there's of course a lot you can do with AI also to help the work of engineers, making these products more usable, defining your models by prompting, and kind of that sort of things, having a trained LLM models that have been well trained with the documentation of the physics simulation tool, and kind of just making engineers' lives easier.
Another thing that actually we haven't touched on yet is that Quanscient is, as you can sort of almost make out of the name, is involved with quantum. So how does this AI play together with the quantum side of things?
So yeah, that's a really good topic, and what we believe that if you look at certain problems like simulation problems, let's say computational fluid dynamics has a lot of these. For example, simulating doing a wind tunnel level aerodynamic simulation of an airplane in cruising speed is something that is an unfeasible feat for any classical compute today. It would take years to compute even with the best-in-class supercomputers. These are massively complex problems. So we think quantum, and we already have a lot of evidence on this, we think quantum is the technology that will unlock these unachievable numerical simulations for today. Now, however, to do a full-scale aerodynamic simulation of an airplane end-to-end requires typically running thousands of time steps, kind of letting the system evolve until you're at a stable condition in let's say cruising speed. Doing that with quantum will likely be quite a few years away. It basically requires fault-tolerant quantum computing, which is, according to experts, we're like 5 to 10 years away from that. But however, what we think, and we have a lot of evidence on this, with let's say 100 high-quality physical qubits and some hundreds of CNOT gates, we could already do a few time steps of this simulation. And now we're starting to look at things which are 2 to 3 years away. And the concept basically is that when you can get a little bit of that super high definition physics simulation data from quantum, and then on the other hand, massive volumes of lower fidelity simulation data from the cloud, combine those for your machine learning training, and that will also enhance the results of the AI models. So it kind of brings the practical industrial quantum advantage closer by combining all these three technologies. And yeah, 5 years away, definitely. That's kind of a big part of what should be available within Quanscient Allsolve.
All right. Well, back to today, back to 2025, end of 2025. Who can benefit of this multiphysics AI right now?
Well, as I mentioned earlier, we have examples on electric motors, on microspeakers, on MUT devices, on kind of piezo material characterization problems, or piezo composite arrays, things like that. So really, companies definitely working in these spaces can benefit, but we're also constantly evaluating and looking at new use cases. So typically, optimization problems where you have a few kind of KPIs that you want to optimize for, and we can still today sort of limit the input parameters for the AI models to a relatively small number, like a dozen or so. Those are good applications for multiphysics AI already today, and there's a lot of problems in that space. So, for example, chip packaging, there could be a lot of these things occurring there, or different kind of electronics applications, antenna design, like RFEM simulations. A lot of potential for new applications.
Well, then very practically speaking, let's say that there are people listening to this episode right now who are working with these industries or these problems, and they want to start using it. How do they go about that?
Well, today, definitely getting in touch with us, with me personally, or just like dropping a line via our website contact form is a great first step. What would follow is that we would kind of drill down on the specific simulation challenges and problems and R&D topics that you have, and look for which are great applications to potentially build multiphysics simulation data lakes, train machine learning models, and then again dramatically speed up the pace of R&D in your organization.
All right. Any final thoughts before we wrap it up?
Well, maybe as a final thought. So many people kind of at Quanscient, myself included, were sort of quite skeptical actually on what the benefits here will be and all that. But once we kind of trained the first models, that was a real eye opener. Like the results were amazingly good. I would say a lot of people in our team were surprised about that, and we've been kind of once seeing that, we've gone all in really generating new examples, generating new models. So it's been there, and I think we're just scratching the surface of the true potential of this technology and how it will change engineering. So I'm really excited to see, like, let's come back to this episode in 5 years and see just how right or wrong I was in my predictions.
All right, we'll do that. But hey, thanks for the episode.
Thanks a lot. Pleasure to be here.
Thank you for listening to this episode of The State of Simulation. To stay updated with the latest episodes, webinars, blogs, white papers, and more, join our community of more than 7,000 engineers and engineer-minded people on our LinkedIn page, Quanscient. Thank you again, and see you in the next one.